SwayamPrabha. Digital India. Educated India.
In the last lecture, we have discussed about the linearized model of the longitudinal motion of the aircraft. And in today's lecture, we'll be discussing how we can come up with the linearized model of the lateral and directional equation of motion of the aircraft. So this is lecture number 41. Let us rewrite the equation of motion of lateral and directional equation of motion of lateral directional motion of the aircraft let us rewrite the equation of motion in this lateral directional motion. Y plus mg cos theta sin phi m into v dot plus r u minus pw. This is the force along y direction and moment in x axis. So in the lateral directional motion, we have to consider the force along y direction, moment along x-axis, and moment along z-axis. So moment along x-axis, we can write p dot ix minus r dot ixg plus qr into ig minus iy in minus ixg pq, and moment along z direction n equal to, so moment, if we apply the moment along z direction, we can control the yaw angle, and if you apply the moment along x-axis, then we can control the roll angle. So moment along z-axis, we can write minus p dot I xg plus r dot iz plus pq iy minus ix ixg qr. This is the equation of motion. Let me define this equation number 1. Equation, nonlinear equation we can write, nonlinear equation. And our main motivation is how we can come up with the linear form of these nonlinear equations. Before we proceed, first we have to consider the linearized model, not linearized model, the trim flight or the steady level flight for the lateral directional motion of the aircraft. So we can write the steady state trim flight for lateral directional equation at we already have discussed the trim values for the lateral directional motion are for the values of P0, Q0, R0 equal to 0 and phi 0 equal to 0. For these conditions, the steady state flight equation for the lateral direction equation, we can write y not equal to m v naught dot and L not equal to 0 and N not equal to 0. So this is the trim flight. How these equations are coming, that is very clear if you consider this trim values, the above equation number 1. So we'll get this trim equation, or the steady level flight of the lateral directional motion of the aircraft. Trim flight for lateral directional motion of aircraft. And let us define this equation number 2. Now we'll apply the perturbation to the different equations in equation number 1, and we'll come up thus a linear model of the individual equation, force equation, moment equation. Now, let's start with the first the force equation along y-axis. So let us write. Let's start with force equation in y direction. Let us rewrite the force equation along y direction: y plus mg cos theta sin phi equal to m into v dot plus ru minus pw. Now we'll include the perturbation to this system, so we can write the variable in this equation. If you consider, there is 2 components in each variable. One is the reference value, another is the perturb variable. So if you consider the perturbations, if we apply, we can write y naught plus delta y, theta equal to theta naught plus delta theta, phi equal to phi naught plus delta phi, and v naught plus delta v, and r equal to r naught plus delta r, and u equal to u naught plus delta u, p equal to p naught plus delta p, and w equal to w naught plus delta w. Including, if we apply this perturbation variable to the equation number 3, equation 3, we can write, including the perturbations to equation 3 yields, we can write y naught plus delta y plus mg cos theta naught plus delta theta sin phi naught plus delta phi equal to m into d dt, v naught plus delta v plus r naught plus delta r, u naught plus delta u, p naught plus delta p into w naught plus delta w. So this is equation number 4. We'll solve this part. So we need to let's solve this part, and how we can find the linear model of this part. Then we'll do the rest of the terms. So let's start with let me define this, the term A. Solving the term A, we get cos theta naught. Let's start with first cos theta naught plus delta theta. Delta theta we can write cos theta naught cos delta theta minus sin theta naught sin and delta theta. And for the small angular displacement, if you did notice, if you consider for small perturbation of, or we can write for the small value of, for small perturbation of delta theta, we can write cos delta theta equivalent to 1 for the small value of delta theta, and sine delta theta equivalent, we can write delta theta. So introducing this variable in equation 5, we can write cos theta naught plus delta theta, we can write cos theta naught minus delta theta sine theta naught. Now we can do the same thing for the sine phi naught plus delta phi. So we can write, let me expand the term sine phi naught plus delta phi, we can write sine phi naught cos delta phi plus cos phi naught plus sine delta phi. And if you apply the same small value of delta phi, we can expand this expression. We can come up the some value for this sine phi naught plus delta phi. We can write using the small value of delta phi, we can write sine phi naught plus delta phi, we can write is equivalent to sine phi naught plus cos phi naught delta phi. If you incorporate this expression, value of cos theta naught plus delta theta and sine phi naught plus delta phi, in equation number 4, we can come up, not equation number, equation number 4 for the term A, if we now, so now we can write the term A, which is nothing but cos theta naught plus delta theta sine phi naught plus delta phi can be expressed as cos theta naught plus delta theta sine phi naught plus delta phi. If you multiply both this expression, we can come up the value of this cos theta naught sine phi naught plus delta phi cos theta naught cos phi naught minus delta theta sine theta sine phi naught minus delta theta delta phi sine theta naught cos phi naught. So these are the value for term A. Again, we can note that during the trim flight condition, we know that P naught equal to Q naught equal to R naught equal to V naught and phi naught equal to L naught and n naught equal to 0. For the trim condition, these are the reference value of these parameters or these variables should be 0. And we can neglect and also neglecting the products of small disturbance, small disturbed, we can write small disturbed variables, which are basically delta theta and delta phi. So if you ignore these terms, and also if you assume this trim condition, so equation, let me define this equation number 6. If you define this equation number, equation 6 can be written as cos theta naught plus delta theta sin phi naught plus delta phi equivalent to delta phi cos theta naught. So this is very nice form of term A in equation 4. We also have to assume the trim values of the force equation in longitudinal motion, which is this equation. Now, if you here, if I consider the trim values of the or trim condition for the force equation in y direction, and if you consider the term A, which is given by this expression equation 7, so we can write using the trim flight conditions, which is basically y naught equal to mv naught dot defined in equation 2 and using equation 7 inequality, equation 4 can be written as equation 4 written as delta y plus mg delta phi cos theta naught equal to m into delta v dot plus u naught delta r minus y naught w dot into delta p. The same concept also we have used in equation 4. We have ignored the multiplication of the part of variables, the product of part of variables. Further, we have to consider another condition. Further, if we consider the stability axis, we know that W naught equal to 0. Let me define this equation number 8. This part already you have done during the discussion of the longitudinal motion of the aircraft. So for this condition, equation 8 can be written as we can write delta y plus mg delta phi cos theta naught equal to m into delta v dot plus u naught delta r. Let's define this equation number 9. Now we have to consider how the delta y, the force, the part of force along y-axis gets affected and what are the variables involved for generating delta y. Let's look. Let me write some note. Side force y is basically a function of v, p, r, phi and delta r. So these are the terms or the variables or the control are actually affect the side force in the aircraft. Also, we need to denote aileron deflection. Aileron deflection has very little influence on the side force. Hence, it can be neglected neglected. So now, using the Taylor series expansion, the part of force can be written as delta y. We can write del y del v capital delta v plus del y del p delta p plus del y del r delta r plus del y del phi capital delta phi plus del y del delta r capital delta r we can write. So this is the total side force, part of side force generated due to the effect of different variables in this equation. And let's define this equation by equation 10. And if you substitute equation 10 in our force equation, part of force equation in 9, the equation of motion in y direction, we can write substituting the equation 10 in equation 9 in place of delta y, you can write delta v dot equal to, we can write 1 upon m delta y delta v capital delta V plus del y del p capital delta P plus del y del r delta r plus del y del phi delta phi plus del y del delta r capital delta r plus g delta phi cos theta naught. Delta term we missed. So this is the expression we are getting for the rate of change of the part of velocity. along y direction. And this expression can be further simplified as yv delta v plus yp capital delta P plus yr delta r, the same way what you have done for the longitudinal motion of the aircraft in the linear form. The same thing we are doing here also. Y phi delta phi plus y delta r capital delta R plus g del phi cos theta naught minus u naught delta R. So this is what you are getting. So where yv equal to 1 upon m del y delta v and so on are the aerodynamic derivatives divided by airplane's mass. This equation, let me define this equation number 11, question 11, can be further simplified as until v dot equal to yv delta v plus yp delta p plus yr u naught delta r plus y phi plus z cos theta naught delta phi plus y delta r capital delta R, and again we can simplify as d dt minus yv into delta v minus yp delta p minus yr u naught delta r minus y p plus g cos theta naught delta phi equal to y delta r capital delta R. So this is the linear form of the force equation along y-axis. If you notice, this equation are linear because the coefficient of all the terms are scalar component, or we can not time varying, or we can say the time invariant. And this system also we can set linear time invariant system because all the coefficient of the equation are linear time invariant. If you notice this equation, it will be very clear because this term, this term, and this term are basically we generally get from the wind tunnel testing for the given flight conditions. And now let's stop it here. We'll continue from the next lecture in the how we can come the linear form of the moment equation along x and z axis. Then we'll finally come up the state space model of the lateral directional motion of the aircraft. Then we can move to the control. Thank you.